All right, yesterday we dealt with double angle formulas. Once again, your familiarity with these problems should be the same types of problems that we've been dealing with. It's just now a different set of formulas that we're working with. Rather than angle addition, you're dealing with double angles. Once again, grades tend to pick up a little bit in this section just because you're sort of used and comfortable, I don't know how comfortable you get, but you're sort of used to what's being asked of you within the problems. You had problems 9 to 30, multiples of 3. I'm going to take a look at one of the trig identities because you're still going to have to do a trig identity. I'm sorry. It's still going to be there, but it's going to be something very similar to what we just see. So it'll be a little bit easier, a little bit more comfortable for you. If we take a look at problem number 30, once again, I would suggest you know how to do a problem like this. Hitting that say no more, you'll see a problem like this again. Problem number 30, we have the tangent of y. We want to make it look like the sine of 2y over 1 plus cosine of 2y. Which side should we start with, left or right? Why? More stuff. That's right. You have more stuff on the right. So if you have more stuff on the right, let's work with the right. Well, this section is dealing with all double angle stuff. So on the right-hand side, we're dealing with double angles. So let's make our substitutions with our double angles. So if we take a look at the top, sine of 2y, we only have one substitution for the sine of 2y. Write it down. What's your sine of 2y? Which is 2 times the sine of y times the cosine of y. Now, the bottom, we have the cosine of 2y. And we had 3 different substitutions for the cosine of 2y. All 3 of them will allow you to get to eventually what you want to get to. Some of them may take you another step or two to do. There's also not a problem by looking at the left-hand side. If I want to get the tangent of y, which by definition, in terms of sine and cosine, I have the sine of y over the cosine of y. If I can get to sine of y over cosine of y, that's going to take me back to the tangent. So what I want to get here is I want to get just 2 separate things here, sine and cosine. Sine over cosine. Well, that sort of gives us a hint of what we want to use for the cosine of 2y. Because ultimately, I want to get a cosine on the bottom. Well, if I take a look at what I have for the cosine of 2y. We have cosine squared y minus sine squared y. I have, let's see, 2 cosine squared y minus 1, and I have 1 minus 2 cosine squared of y. And ultimately, I want to get sine over cosine. Well, if I use this one here, that's going to throw some sines on the bottom. And I want to get cosine on the bottom. So I really don't want to utilize this one. So that gives me these last 2 that throw me into this is cosine and sine, and this gives me just cosine. Well, if I choose this one here. Let's see what happens. What so magically happens to our denominator? Let's take a look at our denominator. I have 1 plus cosine squared y minus 1. Alakababa, shishkumbam. What happens here? And gives us what? 0. They cancel out. This minus 1 just goes bye-bye. Adios. They gone. Leaving us with 2 sine of y times the cosine of y over 2 times the cosine squared of y. And now I have all multiplication, which is great because I can start doing some canceling. What all cancels? One of the cosines does, and what else does? 2. This goes with this. This goes with this, leaving us with sine y over cosine y, which is tangent of y. We is done. Once again, you'll see something like that on your test. Okay, it's just using your double angle substitution. It's a key. The key is making sure that you choose the correct one, that you're trying to use one that helps you out a little bit. Now, if you use cosine squared minus sine squared, which is fine. If you had 2 sine of y times cosine of y over 1 plus cosine squared y minus sine squared y. You made that substitution instead. If you still combine and rewrite 1 minus sine squared y plus cosine squared of y, I have 1 minus sine squared, which we know is cosine squared. So we have cosine squared y plus another cosine squared y, which gives me 2 cosine squared y. So it gets you there. It just puts you on a little detour. Okay, you have to take an extra step to get there. Once again, when dealing with equations like you had in problem number 20 or number 18 and 21, I'm going to throw them into thetas. I'm not going to make you go into x's. You have enough on your plate, as I told you before, not to worry about radians at this point. So I'm going to do everything in theta and degrees for you when you go to problems, solving the equations like you have in problem number 18 and problem number 21. 9, 12, 15 are similar to the ones that we did here in class. If we take a look at number 15, once again, you need to make sure you set up a correct picture. In problem number 15, the picture is half the battle. We're in quadrant number 3. We're in quadrant number 3 and with angle A. So in quadrant number 3, I'm drawing my angle A. Cosecant is the reciprocal of what, Caitlin? 1 over sine. This is 1 over sine of A. Is the cosecant of A. So I can write this over 1. My sine of A is opposite over hypotenuse. So the cosecant of A is hypotenuse over opposite. Okay, what we have to watch out for here. If I would write my hypotenuse as -3 and my opposite is 1, my hypotenuse is always going to be the positive one there. So how can I transfer this into a problem I could work with? The hypotenuse has to be positive, but the cosecant still has to be -3, or the sine -1/3. Yeah, we can turn this around and erase this and make this the negative. Now I have 3 over -1. 3 over -1 is still your -3. Now we have our good old buddy Pythagoras. We have our good old buddy Pythagoras. That's always in our hip pocket. He's always with you. Oh, what was that? What was that? He's always with you. So to find this value of x up here, we have to really watch when I square the -1, -1 times -1 gives us +1. So we can subtract 8. So x squared, or subtract 1, x squared equals 8. X then equals square root of 8, which is 2 square root of 2. Once again, I'm not going to throw, as I said before, you have enough on your plate in these problems not to sit there and throw more radicals at you. Okay, so I'm going to keep it pretty generic in regards to 3, 4, 5, 5, 12, 13 triangles. So you don't have to sit there and worry about radicals as you're going through the problems, because that's a whole nother ballgame for us. But then at this point, I could sit here and go through what I need to go through. But this here was the challenge. This here was the challenge for the problem. Now it's sort of nice when I have the cosine of 2a. We have cosine squared minus sine squared. It wouldn't be bad to go back to that original square root of 8. The cosine of a is negative square root of 8 over 3, because I'm going to square that, and when you square that, it gets rid of your radicals for you. Minus negative 1/3 squared. So we have 8 over 3 minus, or 8 over 9 plus 1 over 9. Makes it a little bit easier. You don't have to re-simplify radicals. Like I said, the problem with this is having to deal with radicals, and I'll take that off the plate for your tests. Other questions you have? As you start to see these problems and you start applying the formulas, once again, you should be a little bit more comfortable with the process. Okay, the radicals throw something else at you. Which I understand. And when you get to next year and you take pre-calculus and trig for college credit, then that's a little bit more fair game for me. But you have a little bit more comfortability in regards to going through the problems, then it's okay to start throwing radicals at you, because you've seen these types of problems already. Okay, we deal with double angles. Today we're going to deal with half angles. We got double angles, we got half angles. What we're going to utilize is the double angle formulas for each of the half angles. The cosine of 2a. One of the definitions of the cosine of 2a is 2 cosine squared a minus 1. This is what we talked about yesterday. One of our definitions for double angle cosine. We're going to let a equal 1/2 x. So wherever I see an a in here, I'm going to put a 1/2 x in. So we have the cosine of 2 times 1/2 x. Half of an angle, I'm multiplying by a half, is equal to 2 cosine squared of 1/2 x. There we are. Minus 1. Now, 1/2 x, that's half an angle. We can also write this as x divided by 2. If I multiply by a half or divide by 2, I get the same thing. Okay, multiplying by a half or dividing by 2, I get half of an angle. On the left-hand side, if I multiply 2 times 1/2, they go bye-bye. We have the cosine of x is equal to 2 cosine squared x over 2 minus 1. Half x, same as x over 2. If we add 1 to both sides, we have 1 plus cosine of x is equal to 2 cosine squared of half x. We have multiplication by 2. We divide both sides by 2 here. I'm just going to write my square term first. So we have cosine squared of half x is equal to 1 plus cosine of x divided by 2. Then to get rid of a square, we can square root both sides. So the cosine of half x, when we take the square root of both sides, when we physically square root to both sides, we have to get plus minus in there. So the cosine of a half angle is equal to plus minus square root of 1 plus cosine x divided by 2. The cosine of half angle. Once again, another thing to add to your sheet. As we did this up here, another double angle formula for the cosine of 2a is 1 minus 2 sine squared of a. Making my same substitutions. Let a equal half x. We have cosine of 2 times half x is equal to 1 minus 2 sine squared half x. Okay, so we're just doing the exact same thing, but we're just doing it with a different formula, double angle formula. Once again, on the left-hand side, I have 2 times 1/2 x. They go bye-bye. The 2's go bye-bye. So this will cancel with this. Leaving us with cosine of x is equal to 1 minus 2 sine squared of x over 2, half angle. Now, our next step, I should patent it, is the process what I call the double switcheroonie. I should patent it. Because what we have mathematics is all set up with processes. You have things that you do, and there's processes that you do, and there's recipes that you have to follow step by step by step by step. Okay? And we have addition property, division, multiplication, square roots, we have all these processes. But this process here, I coined the double switcheroonie process, which allows us, I want to make this positive. To make this positive, I need to take it to this side. But to bring it to the side, this has to come over here. So I got the double switcheroonie, okay? This side, this here is going to go over here, and this is going to come over here. Well, how do I take it? Well, I add the 2 sine squared of x over 2, and then I subtract the cosine of x over here. So what this is going to look like is 2 sine squared x over 2 is equal to 1 minus cosine of x. Because I've added this to make it positive, because it makes it easier when it's positive, and I subtracted this to take it back over to the other side. The double switcheroonie. Now the process is exactly the same as what we just did up above. We're going to divide by 2. Divide by 2. So we have sine squared x over 2 is equal to 1 minus cosine of x divided by 2. Then I need to get rid of a square root. So I go out to the square root tree with my axe and I do some cutting. So we're left with a sine of half x, x over 2, is equal to plus or minus square root 1 minus cosine of x divided by 2. There's your half angle formula for this sine of half angle. Once again, something more to add. And it looks very similar to the cosine, except for now I have 1 minus cosine rather than 1 plus cosine. When I deal with plus cosine, when I have cosine, it's plus cosine of x. When I have sine, it's minus cosine of x. All right, tangent half x can be defined just as sine over cosine. Sine half x over cosine half x. So we're going back just to what our basic definition of tangent. Tangent of A is equal to sine A over cosine. Well, tangent x over 2 is equal to sine x over 2 divided by cosine x over 2. So what we have here is we have plus minus square root 1 minus cosine of x divided by 2 over plus minus square root 1 plus cosine of x divided by 2. And oh my gosh, does that look ugly. Using our properties of radicals. If I have 2 separate radicals that are being divided, I can combine them underneath one radical. but that really doesn't look any prettier. That's still ugly. But I can now use rational expressions. I can multiply numerator and denominator by a value of 2, which makes the 2's go away. So we are left with plus or minus square root of 1 minus cosine of x over 1 plus cosine of x. Which is looks a little nicer. And it's sort of nice because all these things are all just dependent on the cosine. So I don't really need to know the sine, I just need to know the cosine. But there are ways to make this look a little nicer too. There's 2 other alternate forms for the cosine of a half angle. I'm sorry, tangent of a half angle. We go back to what we're equal to. And let's use our property of fractions, equivalent fractions. Our properties of equivalent fractions, once again, to make equivalent fractions, you can multiply or divide numerator and denominator of any fraction by the exact same thing and create an equivalent fraction. That's how we reduce fractions. If you have 3 over 6, you can divide top and bottom by 3 to give you 1, 2. Okay? Equivalent fraction properties. Well, you can also do with respect to that multiplication. We can multiply 2 over 3, 2/3 by 5 to give us 10/15 and get an equivalent fraction. Well, what we're going to multiply by is we're going to multiply by 1 minus cosine of x. Top and bottom by 1 minus cosine of x. So on top I have 1 minus cosine x times 1 minus cosine x, which is 1 minus cosine of x squared. On the bottom, I have 1 plus cosine x times 1 minus cosine x. If we would FOIL this out, we'd have 1 times 1, which is the value of 1. I have a plus cosine x minus cosine x. They go away. Difference of perfect squares. Then I have a minus cosine squared x. That middle multiplication, once again, plus cosine of x minus cosine of x, they go away. So on the bottom, I have 1 minus cosine squared, which is equal to what? 1 minus cosine squared is equal to what? Sine squared. So we have square root of 1 minus cosine of x squared over sine squared of x. Well, both my quantities are being squared. They cancel out. So we're just left with the tangent of x over 2 is equal to 1 minus cosine of x over the sine of x. This is my suggested one that I would suggest to you to utilize. The reason why is if I did have radicals with these things, it's a lot easier to rationalize my denominator when it's just one term in the bottom. Where if I have 2 terms on the bottom, now I have to worry about a conjugate. And that's like, make me gag. Okay? But if I just have square root of 3 on the bottom, I can multiply top and bottom by square root of 3. I can get rid of it. But if I have 1 plus square root of 3 on the bottom, now I need to multiply 1 by 1 minus square root of 3 on the bottom. Oh, okay, that's what it makes you do. My suggestion one. We could also get a third formula. By multiplying top and bottom by 1 plus cosine x. I'm not going to go through the full derivation because it's going to look very similar to this. What this will turn into is sine of x over 1 plus cosine of x. So like I said, if I have a radical that appears in my problem, and I have to multiply by a conjugate, that's lucky. Here, if I have a radical on the bottom, I can just multiply top and bottom by that square root. Makes it a little bit easier. Once again, this is my suggested one to do. Okay, let's look at the problem. Cosine of theta is equal to negative 3/5. Theta is between between 90 and 180, which puts us into which quadrant? Second quadrant. So I'm in my second quadrant. Here's my theta. See, my cosine is negative 3 over 5. My opposite side is a value of 4. I want to find the sine of theta over 2. So we have plus minus square root of 1 minus cosine of theta divided by 2. Well, my cosine of theta is given to me already at negative 3/5. So once again, making my substitution. Now, we can multiply top and bottom by the value of 5 if we want. But also, if you want to put it into your calculator, 1 minus quantity, 1 minus negative 3/5, and your quantity plus you divided by 2. Hit your math button, hit enter, hit enter. It will take you back to a fraction. Quantify 1 minus a negative 3/5 and quantity divided by 2. Hit your math button, hit enter, hit enter. It takes you back to a fraction. But once again, if you want to advance yourself, I can multiply top and bottom by 5. So we have 5 plus 3 divided by 10, which is 8/10. Which is 4/5. So we have plus or minus square root of 4 over square root of 5. Square root of 4 we can do, it gives us 2 over square root of 5. And then we can multiply top and bottom by radical 5. So we have plus or minus 2 square root of 5 over 5. But the other issue that we have to deal with still is this plus minus. We have to make a decision, is it positive or it's negative? I'm trying to find the sine of theta, half theta. If theta is between 90 and 180, half theta is going to be in between what and what? Theta is between 90 and 180. Half theta has to be in between what and what?
45 and 90.
How'd you get that?
I divided 90 and 180 by 2.
Yeah. If I would just take and divide all these using my division property of inequality, divide everything through by 2, I have theta over 2 is between 45 and 90. which puts us into quadrant number 1. Or if you take any angle, I don't care what number you want to pick, between 45 and 90, and take the sine of that angle. So you can click in your calculator. Sine of any number between 45 and 90 is a positive or negative? Positive. So my solution here is going to be a positive. How's the spirit of the wood? Cosine, theta over 2. It's the exact same process. So you have 1 plus a cosine of theta divided by 2. Our cosine of theta, once again, is negative 3 over 5. So sub it in. If you look at the previous problem, all it's going to change is this plus sign right here turns into minus. So this is going to be 5 minus 3 divided by 2. I can multiply top and bottom by a value of 5. So we have 5 minus 3 divided by 2. Divided by 10, which is 2/10, which takes us back to 1/5. So we have square root of 1 over square root of 5. You have 2 over 10. 1/5 is your fraction. You clickety-clack it through your calculator, you get 1/5. Rationalizing this, we have plus or minus square root of 5 over 5. And once again, I can take cosine of any angle between 45 and 90. And you'll see, whenever you're dealing with the first quadrant, all your trig values are going to be positive. If I go tangent, a theta over 2. Once again, it does not matter which one you do. You can utilize either one of these. I'm going to go with the 1 minus cosine of theta divided by sine theta. So we have 1 minus a negative 3 over 5 divided by, now I have to take a look at my triangle. The sine of theta is 4/5. Once again, you can multiply by 5, or if you want to quantify and divide in your calculator, make sure you quantify both top and bottom. It does not matter. We have 5 plus 3 divided by 4. We have 8 divided by 4, which is a value of 2. Now, the nice thing about utilizing this formula, the signs positive or negative will come out in the wash. You don't have to worry about making a decision. It will come out in the wash for you. Okay, you have a little bit early today. Page 128. I'm sorry, 138. Page 138, 139, you're dealing with half angles. Yeah, you're up to 24. You have 15, 18, 21, 24. 4 problems. 15, 18, 21, 24. Tomorrow we'll come in, we'll deal with our last set of formulas. Once again, the end is near. La la la. Adios. Have a good day.